Hey guys, so today we'll be covering a very important topic in mathematics, linear algebra and differential equations. A lot of people who don't take linear algebra, who didn't take linear algebra, struggles a lot with this concept in many math courses. So this is why I think this is a very important topic to master before taking any high-level math courses such as Calculus 3 or differential equations. So the topic we're going to cover is called linear dependence and independence, and this is about multiple vectors and how they're dependent of one another. So I want to start with giving an example. If we have a vector v1, okay, let's assign these numbers to this vector. Okay, this is a 3 by 1 vector. A 3 by 1 vector means it has 3 rows and 1 column, as you can see. And I want to make another vector, which is going to be v2, and v2 can be expressed by c times v1, where c is a constant number. So anytime we can create this relationship between two vectors, there we have a linear dependence, okay? Dependence. So let's give an example of v2 where we would have c times v1 and we could obtain a v2 vector. So since we have a v1 here, if I multiplied v1 with 2 and I multiply this v1 vector by 2 and I got this new vector 2 2 2 2, this 3 by 1 2 vector is actually linearly dependent to v1. It's because you can multiply this vector v1 with a constant 2 and get this vector, and these vectors are related to each other. You can divide this vector by 2 and get the same vector. So they're constant multiplies of each other. Okay, and the best ways to solve these problems, to understand the dependence and independence between multiple vectors, is to start with creating a matrix. Okay, so I want to start with a similar example where our v1 is 1 1 1, our v2 can be, let's say, 2 2 2, and let's say v3 is 3 3 3. Okay, well, as we covered before, we know that all three of these vectors are linearly dependent because of the fact that we can multiply this one vector and get these vectors out of it. So we know that we have to obtain that from the theory we're going to use. So I'm going to put these vectors in a matrix together. A matrix is a group of numbers, entries, and these entries ultimately form a matrix. Okay, this is a matrix, and we're gonna use some operations. We're gonna hold this matrix, this dot is holding, and put these numbers here. So I'm gonna multiply this first row with 1 and subtract it from the second row. Likewise, I'm going to do the same thing, and this is basically called Gaussian elimination, where we simplify our matrix to a more simpler form. Okay, guys? This is completely legal, and this doesn't change the matrix. Imagine this is a x1, x2, and x3, and you have 3 equations. You can basically get the first equation and subtract that from the other equations, and basically that's not gonna change the system of equations, because a matrix is also a system of equations in a way. So now we have something looking like this in our eliminated matrix. We have 2 rows of zeros and a row of numbers. So first thing we want to do is call this a leading entry. Anytime in a row we go from left to right, we encounter a non-zero number. That will be our leading entry. So in this case, our leading entry is 1. Over here we don't have a leading entry on the second row, and on the third row we don't have a leading entry. So this is our pivot column because we have a leading entry here. So this is called a pivot column, and also a basic variable. Okay, so this is, if we call this x1, x2, and x3, this will be our basic variable because this is a pivot column. However, these are non-pivot columns, non-pivot. It's because we don't have a leading entry here. Okay, we don't have any leading entries on these columns. So these are non-pivot columns, and they're called free variables. Okay, the reason why these are called free variables is because we can literally assign x2 and x3 to be any real number in R3 because this is a 3 by 3 matrix. However, x1 cannot be anything because x1 can be expressed. We have the ability to express x1 in terms of x2 and x3. Okay, so because we can do that, and every time we have a pivot column we will be able to do that, it means that this is a basic variable, but these are free variables. Okay, and in the existence of a basic variable, we will have linear dependence. Okay, so if a basic variable exists, there is linear dependence. Okay, very interestingly, this is a very simplified version of our system of equations. So we can consider now these vectors also as similar to these vectors, and we would, if we have 1 0 0, 2 0 0, and 3 0 0 from these columns, we can actually multiply this by 2 and get this one, and multiply this with 3 to get this one. So these constant numbers that here actually also represent your constant multiplication of the basic variable to get these vectors. So it's also helping you understand linear dependence on top of the relationship between these vectors. So I want to now give you an example where we don't have linear dependence, we have linear independence. For example, if this was, let's call this matrix, okay? Let's think about this vectors, okay? Let's call this v1 and let's call this v2. So over here I have a 1 0 1, and for v2 I have 0 1 0. And although I could multiply v1 with 0, there's no way I could convert this 0 to be 1. So it's, for me, impossible to get v2 out of v1 using any number. Okay, it is not possible because this is not gonna work out. Impossible. It's just physically impossible. So when you have that, this is called linearly independent. Okay, linearly independent. Okay, we can have linearly independent many different matrices. For example, this is going to be linearly independent to both of these, and all three of these are linearly independent for the same reason. They are linearly independent. So to figure out the linear independence, we're going to do the same thing, build that matrix. Okay, and then once we have this, we're going to reduce the form. So this will be just like this, and we will have this matrix just like this, and this is called the identity matrix. Okay, the identity matrix, and we have 3 pivot columns, 3 pivots. Okay, and that means that we have 3 free variables. Okay, 3 free variables. So since we have no basic variable, basically this is a linearly independent because there is no basic variable. Okay, so also, even if we think the same way, we reduce these vectors and get these 3 vectors, 1 0 0, 0 1 0, and 0 0 1. There's no way you can still get these vectors out of it, which actually verifies the point that these are linearly independent vectors. This is the way to understand linear independence and dependence using Gaussian elimination. However, there is one more method where you can take a determinant of a matrix, okay, and that determinant will help you if the determinant is equal to 0, okay, of a matrix. Let's call this matrix A. if determinant of A is equal to 0, that's where we have linear dependence. Okay, but if we don't have 0, if determinant of A is equal to some function or some number, let's call this, I don't know, p of x or whatever, okay, it doesn't matter. If a determinant equals to something, this means that we have linear independence. And for reference to differential equations, when we have independent solutions, okay, if we have a solution y1 and y2, and if they are linearly independent, we can add these functions to fundamental sets of solution, and we will get really neat results. We can use these solutions individually. However, if we have linear dependence, let's say y3 and y1 are linearly independent to each one another, this doesn't create a fundamental set of solutions. So you can either have y1 or y3 in your solutions. Okay, there's no way you could have both because they're technically linearly dependent, so they're the same. That's how you should view and understand these concepts of linear algebra.